Hey Marcus, I'm kind of sending you this video to kind of help you wrap your head around my dispersion wave rocket. In my paper, I talk a lot about a string compass, and so rather than just throw it out there in the abstract, I wanted to give you a first-hand view of what a string compass is. This device was introduced to me when I was a kid by a science teacher, and it's called a string compass. At least that's what I call it, and I think most of the folk out there familiar with it probably call it the same thing. Is that it's just a magnet, right, tied to a string, and one side of the magnet is painted. Let's say that this here side is the north pole of the magnet, and the other side is the south pole that it's not painted. And what happens is, if you leave the magnet to swing free by itself, it will line up with the south pole, right? Nothing amazing about that, but like I said, as a child, I was just fascinated by this thing, and I've been studying it ever since. But what makes this thing such a fantastic mental aid is that if you add a second string magnet to it, the two polarize each other and attract each other. Now, polarization is a fancy word that gets thrown around, but for me, polarization just means that the poles align themselves. But they align themselves north to south, okay, much like the string compass by itself. But what's really fascinating is that if you take one string compass and rotate it, it causes the other to rotate in the opposite direction, synchronously. Now, obviously, this is not a particle accelerator, but that little action right there just has so much physics involved in it. You've got Maxwell equations that kind of halfway explains it, but unfortunately, there's some things in Maxwell equations just don't seem to explain. The one thing is that when these magnets are rotating, there is a longitudinal component and a transverse component. Now, Maxwell equations are good at explaining the transverse, but they do not predict longitudinal waves. But even more so than that, the waves that are being produced have a speed at which they travel, and that's where, I guess, relativity comes in. According to Einstein's theory of relativity, the waves can only propagate at a fixed speed, and that is the speed of light. All right? So if they are indeed propagating at the speed of light, if I rotate one string compass, there should be a frequency at which I reach where the magnets are no longer attracting each other, but are actually repelling each other. And that is the key to everything. Reaching that frequency or rotational speed at which the magnets stop attracting each other and start repelling each other. And that's a mouthful. But if you study Maxwell equations and you study relativity, you should have no problem wrapping your head around what I just talked about. And like I said, this is not a particle accelerator, but it is a mental aid that you can afford, and you'll go leaps and bounds into physics, and you'll see a lot of loopholes that these guys use without explaining what's really going on. Signing out.